The shape of our domain is often related to its overall performance. For example, when we looked at the effective diffusivity through a porous structure, when we consider fluid flow past obstacles, when we're considering elasticity, the shape kind of determines how that multiphysics is present in the material and how it manifests on an overall scale. So what we're going to do today is we're going to look at three different methods of optimizing the shape of a bar, basically, that's supporting a weight. We're going to be applying a load, right? So this is our geometry. This part over here is fixed, and we're going to be applying a load that kind of goes like this over here. And what we're going to be doing is, well, when you apply the load, of course, this is going to displace downwards. We want to fix the maximum displacement for that. But what we're going to do is we're going to make this bar as light as it possibly can. So there are lots of applications. This one is for light weighting, effectively, right? Additive manufacturing is very, very keen on this. This is a great application of that sort of thing. But you can see where this sort of stuff gets more and more and more, especially when we start to incorporate more physics into our models. Okay, so the first way that we've already touched on before, and that is to do with parameterizing our geometry. So if you can see here, this bar is actually split into two at the bottom. There's one point here, there's another point here, and what we're going to do is we're going to move these points up and down. So these have been parameterized, this entire geometry is parameterized, but in our global parameters, we have y_1, which is the y coordinate of this point, and y_2, which is the y coordinate of that point. When we go down here, we can look at the parameter optimization, and if you look into this, what we're going to be optimizing is we're minimizing the mass of our object, so that is our volume times its density. We're going to find the minimum of that. We are going to do that by adjusting the y optimum values of that point and that point, and we have a constraint now. And our constraint for this optimum is that the total displacement over here divided by the max displacement has an upper bound of 1. That's a fancy way of saying that your displacement has to be less than your maximum displacement. Okay, when we go and we solve this, what we're going to see is that's our boundary load over here. These points are moving up and down, and we're calculating the objective. The objective is the mass, and this is what we're trying to minimize. And as you can see, we're going to find a solution. That solution is 365. So remember that number. I wrote it down, right? What you can see is that it did find the optimal value. That's great. What I want to draw your attention to, though, is that the lines here are still straight. And if we zoom in on the mesh is still pretty high quality over here. So what we've done at every single time step, we've changed those parameters. We've redrawn our geometry. We've remeshed the geometry, which is why it's a good quality mesh, and then we've solved it. We take that data, we find the direction that the optimum lies in, and we move in that direction subject to the constraint. And that's how it works. In this case, we only had 2 degrees of freedom, right? y_1, y_2, so it converged pretty quickly. It's also a very easy conceptual model to understand how that's working. Okay, let's see if we can do better, obviously, hence the point of the video. So the next thing we want to look at is something called shape optimization. And shape optimization is a little bit more general. Effectively, what we want to do is we want to tell this material that we're going to be changing the shape of this block. How? We are going to make this boundary into a polynomial. Okay? Remember that there are 2 edges here. Oops. Right? There's this edge here. There's this edge over here. Both of these are going to be modeled by second-order polynomials. Right? This is fixed to this boundary. This one is able to float. All that's in your controls there. You can check out the equation if you want. Okay? Otherwise, the optimization is set up very similarly. We've still got the same objective. We're minimizing the mass. We're subject to this constraint. And let's take a look at the progress while we're optimizing it. Yeah, here we go. So what we're going to see now, because we have a quadratic polynomial, the second order Bernstein, all of a sudden now we're going to have curved shapes. Okay. Meanwhile, what's actually happening in this case is that we're not redrawing this geometry at each point. Rather, we're moving this boundary, this polynomial boundary at the bottom, and then we're deforming our original mesh to conform to it. So this is another application of frames of reference, which you might remember from the past lecture. And here now, instead of a moving frame of reference, we're just deforming our geometry. The mesh hasn't changed, and that's important because when you zoom in here, you'll see that all of a sudden our mesh looks very different. It looks poorer quality because it is actually poorer quality. These thin elongated elements are inferior in terms of arriving at a numerical solution. But the benefit to this is that we don't have to remesh at every time step. At every iteration. So you're going to see that now we have curves, but actually overall the shape looks very, very similar. You can also consider that technically a line is a type of second order polynomial, right? The leading term is set to 0. So that fact means that if the line were optimal, if a straight line was optimal, we should also arrive at it using this method, which we don't. And if we look at the value of the minimum mass, we get an optimum of 358, which is less than 365. So we benefited from this. Coming back to the fact that these are very similar shapes, let's be even more flexible. And this is really cool. This is a really cool study. What we're going to be doing is something called topology optimization. Topology optimization adds in a new field variable into your model. So in this particular case, we're solving for the y displacement, the x displacement. We get our strain, we balance our stresses. In other models, we would look at the temperature, right? T is our field variable, concentration is a field variable, velocity and laminar flow is a field variable. We're adding in a new field variable, which is our density. And our density is really simple to understand. It's 1, where your material is actually present, and 0, where it's not present. Right? Pretty straightforward. And in between you have some kind of an interface going between them. The logic behind it and the way that it's designed kind of is a little bit advanced, to be entirely honest. Filtering controls the feature size of your solution. So it turns out that if we just unleash this without any control on feature size, we're going to get very, very fine features to the point of fractals, right? And fractals, we're not going to be able to resolve that in any meaningful way numerically. So we use these filters to smooth those out. Typically, this is size determined by our mesh. There are good reasons for that go into the numerical methods that we haven't talked about, so on and so forth. Okay, prescribed material is this one since we're not changing that one. When we go into the topology optimization, all that was set to defaults, by the way. When we go into the topology optimization, again, we're minimizing the mass. We're subject to our constraint, nothing new. Now, when we go and we solve this, check this out. The material is now considering every point in this domain to be a degree of freedom. And it's trying to find where it can set some of that material to 0. Which effectively cuts out part of this material. So what you can see here is that it's establishing the optimal shape. Now this is different from the other models because our topology of our shape has changed. Previously, one edge fits together with another edge, and that connectivity doesn't change. But here's very flexible, right? You can see these kind of exotic triangles that are forming here. If you zoom in on the mesh, first of all, you'll notice that our mesh isn't deforming. And the reason for that is that we're not changing our geometry. What we're changing is the density of this material at any point on that mesh, which makes it much more flexible and kind of gets away from this topological problem. And lo and behold, we get a result. And if we look at our optimal mass, we get 26. 261 compared to 358 or 365, right? So this is a much more lightweight material, Luckily for us, this sort of thing is prime for additive manufacturing. One other thing that's really nice to see about this, though, is that it's found triangles. This is a truss, right? Anybody who's ever built a popsicle stick bridge has learned that triangles are the strongest engineering shape. Well, here it is mathematically emerging from this optimization. That's really cool. Really, really cool.